Last section in this module. Don't let the formulae fool you. I'm going to talk you through them, and then I'm going to calculate a couple examples, lickety-split, and then we should be good. This is the same confidence interval we've been doing. The only difference now is that instead of looking at the mu for a single population parameter mu, or a single population parameter p, we're now comparing the difference between two groups. And this is a very natural thing to do. For example, maybe you're conducting a medical study and you're giving some patients a placebo sugar pill and you're giving other patients a new drug. You'd like to see if the average blood pressure goes down based on what you're giving the people. Obviously, you would hope to find a difference between blood pressure measurements if you're trying to design a blood pressure pill. In real life, since we've been taking care of blood pressure for a while, you probably wouldn't give them a placebo. You would probably give some people the new medicine and some people the old medicine, and you'd hope to find a good difference between the two. Same thing with percents. Maybe we're interested in calculating the percents between different candidates. We talked about last time, political candidates. Is there really a difference between candidate 1 and candidate 2? Well, let's subtract their 2 and try to figure out, do we have a real difference between these? You have to watch out for one thing in this section, besides more complicated formulae that have more spots to plug in. You have to watch out for whether our data are independent or dependent. So two possibilities. Let's chat through dependent versus independent data. Independent data means that the people in the one category, the people being used to calculate the one set of values, have nothing to do with the people being used to calculate the second set. They don't interact, they don't have contact with each other, there's a big separation there. Dependent data, on the other hand, involves when you've got the same person in each category. So let's consider. Maybe before the midterm I taught one way, and after the midterm I teach another way. It's not happening this semester, but it could. Some classes it has. If I wanted to say, did students do better on the final or the midterm, as I calculated that, we would be comparing your midterm score to your final score. That's definitely dependent data because it's the same you. I didn't change you, I just changed me. Same thing happens sometimes with medical treatments, right? Your doctor tells you to lower your cholesterol. You start eating oatmeal, but that's not enough, so then you get put on prescription drugs. Try to tackle that a little bit more rigorously. That's dependent information. If the information is coming from the same group of subjects, separated by time, we cannot use these methods on it. I'm today talking to you only about independent data. Totally different group here, totally different group here. We still would like to compare them. Totally independent data could be things like this hospital's staph infection rate versus this other hospital's staph infection rate. As long as the two hospitals were very separate, and as long as we were expecting no patient overlap, we didn't have doctors with visiting privileges at both sides who are secretly being some kind of typhoid Mary, right? So maybe you'd be comparing Texas hospital versus California hospital because those are far enough separate we probably don't have the same surgeons going in between the two places there. So we need independent data for what we're talking about today. And we have this. I have the average score on an exam for a face-to-face class and an online course. Same course, same semester, and so I'm guaranteed that you don't have two people enrolled in both face-to-face and online stats. That's not how it works here. So we know that those are separate. We're able to take a look at those. Notice the first list of data, again I've grabbed 10 points. I've had these auto-generated, so these are not real student scores, but they're close to maybe things that might be true. 66, 49, 72, 60, 67, 75, 95, 70, 77, and 39 for this first face-to-face row of students. Notice so much variation here. It goes as low as 39, it gets as high as 95. Face-to-face classes might have a lot of turbulence in their data. Generally, I find this is because in face-to-face classes you sometimes have students who don't show up and you have students who show up and they attend office hours and they attend tutoring and there's a lot of support. Maybe that face-to-face students are actively, easily able to engage in campus because it's very easy if I have office hours after lecture for students to simply follow me to my office. Online students, you see a lot more uniformity because online students generally tend to, maybe this is a little more uniform than usual too, but online students tend to have the same set of video lectures, the same set of notes, And because they're online students, they're often very similar demographically as well, meaning they tend to work and they're doing this stuff at nights and weekends and around kids, and so you see a different type of performance occur sometimes, a little bit different possibly. So we have the question, is online different from face-to-face? Now these are entirely randomly generated numbers. I've just given you some hypothetical reasons why there might be a difference. For legal purposes, I should tell you that Victoria College cares about your education, and I care, and consequently the two courses are cleverly designed to have similar student success rates, and there's a wide variety of supports possible for both venues. That being said, you should show up to office hours, and if you're online, you should show up to office hours. And if you're online and you can't possibly show up to office hours because you're one of my students in Alaska, then you should send me emails and pretend like you're showing up to office hours. But that's enough of that because I am on a time limit here before my battery dies on the camera. So, without further ado, let's take a look. With just this raw data, I might ask myself the difference, the question, is there a difference? And let's say that this is for spring 2014. Very limited sample data, only 10 in each. Is there a difference for the whole population ever, all time? Well, it's time to do a confidence interval. I only have sample data. Let's pretend I haven't taught this class 16 times, 16 semesters, I don't know. I've taught it 16 times at least. That's probably over the last 4 years or so, 5 years. At least twice a semester. So what, 2 times 4, 4 times, close to 20 times now. I've taught it a lot. Let's pretend I haven't done that. I have a completely blank slate and I'm looking at that and I'm like, oh no, let me do something. If I'm asking is there a difference, probably I want to do something like say at the 95% confidence level. You know what, we've been using 95 a lot, so let's do the 90% confidence level. Incidentally, for education, sometimes I see confidence levels as low as 80% because we don't really do a controlled hypothesis environment, but generally for psychology and whatnot, confidence levels of 95% are more common. For medical stuff, no, you start to get into the 99% confidence level. Stretches that interval a little wider, but there you go. Well, okay, we want to do this. T-scores or Z-scores? I know it's not this proportion business because I don't have information here that lets me build a proportion, at least not yet. And so definitely we're talking about raw data numbers, and so we're going to be talking about X bars as our point estimators. Let's go ahead and label face-to-face group 1 and online group 2. That way you know which X bar we're talking about. Well, you have raw data. It's time to get X bars. You can stall for time and calculate the X bars if you like. I've already entered both these terms into our calculator, into our data button. So I'm going to just hit second in statistics in one variable. And the first time I'm going to go through, and when I do that, we're going to select list 1, frequency 1, and go ahead and calculate. And you can see the X bar is 66.5. Let's go ahead and stick that right here. X1 bar equals 66.5. But then I'm going to hit second and quit. And I'm going to hit second and data again, go to the same one variable statistics, but now I'm going to select list 2. Frequency still 1, calculate still good, and this will tell me my calculation for the other. I am getting x2 bar equals to 66.6. Doesn't look like a lot of difference between those averages, but remember we're talking, about populations rather than other things. Okay. We would like to find out if there's a difference between the populations, if that makes sense, yes or no. We've got our calculation here between these two groups, and so we can calculate x1 minus x2. x1 bar minus x2 bar is going to equal 66.5 minus 66.6, and that's going to equal negative 0.06, 0.01. Can't count. Don't let a negative difference fool you. That just means that the face-to-face students had a lower average than the online students. I picked face-to-face first, I picked online second. If we had switched that order around, we'd have positive, so don't let the negative mess you up. Alright, truth time. Which one of these can I calculate? Well, the question should be, could I calculate the sample deviation? Well, the answer is absolutely, of course. Your calculator just did it. In fact, it was right under that x bar. So, yes. So maybe the follow-up question is, do I happen to know the population information? And the answer gets a little dodgy. You and I right now are just looking at the same set of numbers, so pretend like I'm out of the picture frame, because I, of course, secretly happen to know things about my classes. Just looking at this board, can you find sigma anywhere? My head is not on the board currently. That means you can't find population sigmas anywhere on this board. We don't have the data to give us that. It's safely locked away in my mind, and I've done my best to delete it. So, we have to go with this calculation first. Okay, that works. To do a successful t calculation, we need to know the standard deviations for each of these. That's possible, again, going into data and grabbing those numbers right under the x bars. S1, S2. All right. Data, one variable, statistics, list 1. S1 is going to be about 16.1331267.2. Probably keep on going. If we go to one variable statistics and pick list 2, we find our standard deviation is approximately 2.170509413. Notice the drastic difference in standard deviation there in those two. That's because, like I said in this hypothesis, possibly the face-to-face students have more of a variance depending on what support features they engage in. Online students are generally, they go to work, they have their families, and then they get right to their studying stuff. They're very consistent with their studies, possibly. So, we have this information. That's just about everything we need here, except I should talk to you about TC. Remember, TC requires us to look up the student t-distribution. If you take a look at the student t-distribution, now's a great time to remind you that for that to be successful, we need to know degrees of freedom, and we need to know our confidence level. We chose a 90% confidence level, so I'm going to go here and I'm going to look at the column with 0.9. But for degrees of freedom, we've got two options. We want to take the minimum of whichever of these groups is smaller. Now in this case, I had 10 people in each group. So there were 10 people in the face-to-face, 10 minus 1 is called 9. And there were 10 people in the online, 10 minus 1 is called 9. So pick the smallest number between 9 and 9. Well, it's 9. But you wouldn't have to have the same number of students in each class. In real life, in fact, my face-to-face has more students than my online section does. So I would take the number of people in the face-to-face minus 1, the number of people in the online minus 1, and whoever was smaller, that would be your degrees of freedom. In our case, 9. So let's go ahead and take a look. Alrighty, 90% confidence interval, go down all the way to degrees of freedom 9, 1.833. Now we can calculate our confidence level. x1 bar minus x2 bar minus e is going to be less than mu1 minus mu2, which will be less than x1 bar minus x2 bar plus e. So if we can calculate error, we're doing pretty good. We know that this is 1.833. We know what S1 is, we know what S2 is, and we know what N is. It's 10 in each case. So it's now time to pop that all into our calculator. Let me see if I can type it in one fell blow. Alright, so I have 1.833. 1.833 is my first term here, times. And now I would put parentheses, except we're going to put a big square root bar here, and that's the same grouping as parentheses, so that's alright. So I've done square root, which is second, and square root button there. And now, I am going to put each of these guys inside parentheses, and I'll use a fraction bar, and that'll be good enough for me. So I'm going to go ahead and put parens, fraction bar. On the top I have S1, that is 16.133. 12672. Close parentheses, quantity squared. On the denominator of that I have 10, because there are 10 people in the first group. Go to the side of this, type in a plus. New set of parentheses. New fraction bar. New standard deviation. 2.170509413. This would be a great place to use my calculator's memory feature if I was that clever. Quantity squared, close parentheses, go down to the bottom. Again, 10 people in here. I think I successfully entered it. Get all the way to the out and hit enter. Oh no, I've got a syntax error. That's horrible. I don't know what I did. Let me see here. What on earth happened? Aha. I didn't successfully do my parentheses well. Let me see here. I might be able to fix that. If I hit delete, then close my parentheses. There we go. Oh no, still a syntax error. Because I still am not doing my parentheses all that well, really, am I? As you can see, I almost never use calculators. I prefer Excel drastically because rather than crazy syntax error, it just tells you right away, and then you can fix it. This is probably because I stupidly did many things. Plus fraction bar. Alternatively, if you don't want syntax errors, you can use order of operations to calculate this, which probably is what I should have done in the first place, but 2.170509413. And of course also if I did, if I used the memory feature in my calculator, life would have been a lot better. Alright, I can't possibly fix this equation, so now I'm hitting my reset button. Also panicking because my calculator camera is running out of time. But anyway, we will try this one more time with me typing in things just a little better. I'm going to calculate these terms one at a time in here. So actually I'm going to use fraction bar. 16.133126672. It's quantity squared, all divided by 10. I'm going to go ahead and let that be calculated. My calculator is giving me 26.02. That's this term. Plus, and I hit the plus button then, and when you hit plus and you've got a quantity, notice your calculator picks the previous answer. That's pretty clever. So now I can go ahead and do this calculation. Again, fraction bar, and on the top I can type 2.17050509413. Quantity squared, all divided by 10 again. Do that again. Add those together. Now I've got a number that's 26.49 with a whole bunch of 8s. I'm going to stick that under a square root, which I'll do by storing it into memory position x. And so then I can hit second and square root, second and recall, and pick x. Hit that. That calculates this piece. There we go. Multiply this times 1.833. And I'm getting the number 9 for E. 9.4357. Again, we can now, at this point, finally start to round things a little bit. This number E is what we add and subtract to this difference right here. So if I have 0.01, then I'm going to go ahead and subtract 0.01 minus 9.4. So I get 0.01 minus 904, and I get a negative 9.45 with rounding. Again, don't let a negative difference fool you. That's the left side. Now we do the addition. Again, negative 0.01 plus 9.4. So let me type in to my calculator, 9.4357 plus, adding that to negative 0.01, 9.4257. Notice this one is positive. What does that mean? We took the difference of two numbers, and on a number line, the difference between those two numbers, and let me round this up to 3 decimal places here. negative 945, positive 9.43. Our question was there a difference between online students and face-to-face students of any significance? We see that their averages are pretty close together, but we also saw that the overall turbulence in their data, the standard deviations, was actually quite different. So was that enough of a turbulence? Did that create some sort of difference for us? And the answer is, it doesn't seem like it did. Because when we took the two differences of the population measures, remember, these are point estimators. Our point estimators were pretty close together, but we're saying, well, what about the population as a whole? What's the population as a whole doing? And the answer is, the population as a whole is varying. Maybe it's down this distance, maybe it's up this distance. The online students have a turbulence of plus or minus 2% maybe to their scores. The face-to-face students have a turbulence of plus or minus 16% to the scores. We're calculating these two differences together and saying, well, plus or minus 9 seems to be the difference between these two. This is a very interesting thing we've done, because notice our range for the difference between the two is actually a range of 0, that includes 0. This will be very fascinating in the next module when we start talking about hypothesis testing. But what does it mean if the difference between two things is 0? If I owe you $9 and pay you $9, the difference between what I owed and what I paid you is 0, and that means I owe you nothing. I'm not quite sure where the actual population measures fall, but it's entirely possible that they fall on 0, which means there's no real difference. So I can look you in the eye and say, it doesn't matter whether you take a face-to-face or an online class with me. You're going to have the same educational experience. Yes, some might be more turbulent than the others, but it's going to be about the same, statistically. Let's just suppose, and I think I have enough time to do this, let's suppose that I knew a little bit more about this scenario. Let's suppose that I actually knew the population deviations, which I do. I do because I created them, but more importantly because I taught the class a lot of times, and so I happen to know. If I know, then I might have given us more data and said, by the way, sigma 1 and sigma 2 are equal to 12 and 2, respectively. Notice, sigma 1 for the population of all face-to-face students is 12. The sample, it was 16. Seemed to be a little more deviation in the sample. For the population online, plus or minus 2, seemed to be 2.17. Again, a little more deviation in the sample. That's expected. We expect samples to have a little more deviation because we have less data to work on. We don't have enough to control that. If we had this information given to us, it would no longer be this kind of calculation. We wouldn't have to do it. Instead, we could do this one because we had more data. This is a perfect example of the one scenario, really, maybe like 15 scenarios, where you actually happen to have sample data, spring 2014 information, but you still have a good idea of what the population stuff would do. Because I don't expect the variance between online and face-to-face classes to change all that much. It should probably be the same as it was last time and the time before that. So when you're doing a new study based on old results, or again, think of the doctor scenario with blood pressure medication. We know how blood pressure varies. We don't expect it to change all that much. We could still find out if a new drug is outperforming an old drug. In this case, you would do the entire same set of calculations. This wouldn't change. The only difference, I can find my Kleenex eraser here. The only difference is we don't need to talk about S anymore. So when we calculate this all out, we're doing our 90% confidence level, we could plug into this formula. That would mean we need to know ZC. If you want 90% confidence interval, this is a very bad normal curve here, but you want 90% in the middle here. That means you got 10% on each side, so 5% on each side. That adds up to 100%. So we'd like to look up 0.095. We'd like to find all this area to the left and get that ZC score. If you look that up in your ZC chart, you'll find out that a 90% confidence interval is 1.645. So your number that you multiply in front of here is 1.645. Sigma 1 is going to be 12. Sigma 2 is going to be 2, 10, and 10. With more powerful population information, we can plug that into our calculator as well. And I have 12 squared is 24, so 1.645. I'm going to try once again to make this be one single calculation in my calculator. 12 squared is 144 over 10, plus another fraction bar, 2 squared is called 4 over 10. Calculate that. E is equal to 6.32. Say 6.33. Again, my difference here is negative 0.01 minus 6.33 is less than mu1 minus mu2 is less than negative 0.01 plus 6.33. If we do this calculation again, we're going to see that if we do the subtraction, 6.34 negative and 6.32 positive, once again the difference includes that number 0, so we tend to tell ourselves, I don't think there's a difference. Because I tried to take the difference, I found a confidence interval for the difference. A confidence interval I am 90% certain contains the actual difference. The difference might be a little negative, in which case that would mean that the face-to-face one is in fact truly lower than the online, in which case if the actual number's here, then you start to think, well, maybe I should take an online class. That seems to be better. On the other hand, if it's over here, the true difference is over there, then you say, well, that maybe means the face-to-face minus the online is giving me a little bit of a positive thing on the real population, so that probably means I should take a face-to-face course. If you thought either of those things, that sort of might be true, but kind of not really. Because remember, relationship in statistics does not create a cause and effect scenario. We will make a bigger deal of this once we reach Module 9, but I can tell you right now, if these numbers were true, they roughly are, I'm quite confident telling you there's no statistical difference between my two classes. It's not just because zero's in this interval, but that's a big part of what makes me convinced of that. But the main difference is this. Different students take the different classes. An online student, by and large, tends to be working day shift somewhere, so they're unable to make a face-to-face statistics class. Online students tend, by and large, to have slightly larger families than my face-to-face students have. Online students tend to have more limited time to study for courses, but they counterbalance this by tending to have more life experience. Online students tend to be a little bit older than first-time face-to-face students. All of this means is that math is about practice. Statistics is about practice. Online students tend to have a little more life demands, but they balance this out by having a little more life experience. So they have a little more practice already. Face-to-face students have a little bit less life demands, but a little bit more time, perhaps. And so they're able to balance this out. And once again, you see that the difference between these two courses is, well, quite possibly 0. These numbers are, I did auto-generate them. I didn't want to take real student data. But I can tell you that they are very close to being true-ish. And that means that it's, again, no matter what venue you take, all about the practice. My camera is telling me I'm just about out of battery, so I think I'm going to stop right there. I am going to tell you to practice. I'm going to tell you to go ahead and look at the book section in this section and find another calculation for p-scores. But notice how similar they all were. You plug the numbers into the charts and you add and subtract them. That's what we've been doing all of this section in Module 7. Keep on doing that. You'll be just fine. Don't let the more points to plug in confuse you. The more you know about your formula, the easier it is to read a word problem and say, I don't have all the parts. And then review and rewind this tape. Rewind it. I'll just actually slide back on YouTube. See how I made the difference between when I had to use this And when I gave us that extra piece that let us calculate z-scores and normal instead of t-distribution. Get comfortable with that difference. Read through the problems in this section and see which ones require t's and which ones require z's, and go find yourself a problem that also involves that probability. Until next time, when we start talking about confidence testing and the null hypothesis, I'm going to say be safe, study hard, and I will see you in a very exciting chapter.